towards shallow water, the time cycle is getting increased. And this dots represents some experiment data. So the focus model, simplified model, is showing good compromise, fairly well compromisation with the experiment data, I guess, in this case. So this is one way to measure the maneuverability in shallow waterways. But in this case, the experiment data were limited between very few water depths. So to measure the maneuverability in different ranges of water depths, we need some theoretical approach or some numerical technique in this case. So first of all, I'll go through some of the analytical techniques that are available, give you some idea why I went for the numerical technique later on. So here, actually, there are lots of theoretical approaches that are available, and these three approaches are the most significant one, and these are being used for a long time, and lots of researchers are being done so far on these things, on these theories. So first, I'll go through some basic ideas about these theories. Here we can see a schematic diagram of floating object which is surrounded by an unbounded fluid, and you can see the boundary conditions that we try to impose on the equations of motion and try to simulate the ship behavior in different conditions of waterways. You can see the linearized free surface boundary condition, and in this case we always try to consider the irrotational and implicit because viscosity we cannot consider in this case. And for shallow water effect, we consider the single condition in this way. And our main intention is to find this term, velocity potential, most of the time. So, in case of slender body theory, the assumptions are that the length of the ship is quite high compared to the breadth and draft of the ship. And this slenderness parameter, which is the ratio between the draft to length of the ship, characterizes the whole theory, basically. Using this slenderness parameter, we try to verify the value of the velocity potential. But the main disadvantage of this method is that it cannot predict well for the low frequency ship motions because we are considering a linear stream boundary condition as well as we are not considering the viscosity in this case. So, in this case, maneuverability cannot predict well for the low frequency ship motion, which we need for maneuverability information. And there is one stream theory which considers ship to be composed of strips, and we try to take into account of the interaction between the strips and we measure the process by these equations. But in this case, the disadvantage is that for power motion, we cannot predict the flow quite well, so we cannot use this method as well for maneuverability prediction. And there is one leaching line theory proposed by Pankov, which is kind of like very practical theoretical analysis, which is not all practical. So for this purpose, as I'm not considering we are not considering the viscosity effect in the slender body theory or other theoretical approaches, I went for some numerical technique. Here you can see the flow behind a stair, which is like some experiment data done by Sakamoko, and some advanced vortex method after applying, we can simulate the flow field behind the stair, as you can see, for a longer time, non-constant time simulation. And you can see that this one is for Reynolds number 1000, and this flow shows for Reynolds number more than 600. So as the time passes, the flow behind the stair is getting similar to the flow behind the stair. So using this method, we can predict the flow field behind the body and as well as the pressure distribution. So I will just skip some of the theoretical parts, but this equation is very important actually in this case. It represents and here you can see the flow field is actually discretized into several vortex blocks, which I'll show you later. And by this equation, actually the flow of the vortex blocks are governed, and this represents the convection velocity, which is the vortex blocks are getting generated on the surface, and this one shows the viscous diffusion. So this is the main I'll just try to keep this slide. And this slide is quite important to understand my research, where you can see that this vertical height represents the velocity distribution within the boundary layer, what we are considering linear. And after this boundary layer, the vortex box are getting generated. This is the main technique involved with this vortex level. And this vorticity layer height is basically measured through some experimental data for flat plate. And here the mechanism how the vortex box are getting generated and shown. So this vorticity layer height is very significant to understand the viscosity effect in case of this advanced vortex method. And in case of SO saga, we try to apply this for the ground, hull, propeller, and rudder. And in case of the surfaces like hull, propeller, and hull, rudder, and ground, we consider the surfaces to be composed of force distributions. And using parallel methods, we try to measure the process. And for propeller, we try to use the stick model focus diagram of the cable, and to take this account of free surface effect, we consider the double hull model. After doing the simulation for a drifting ship, we figured out that when we are considering the vortices layer height to be defined by this equation, the vortices are scattered behind the hull. But we have shown that for slender body ship, the vortex shading is quite compliant with the flow behind the ship. So we try to modify this vorticity layer thickness, and we showed that when it is like 0.005, the floating quite realizes the actual floating behind the ship. So here I'll just show you only one slide. So the cable uses this method. So for straight having ship, the velocity is behind the propeller. And from just the last proposal, we can see that if we can predict the distance component of the wave properly, we can measure the interaction coefficient, which is my main purpose to understand. So the conclusion is that we can draw from this point is that multimodal processes are still the most reliable means for the prediction of the maneuverability and water wave. And analytical analysis for the maneuverability and cluster planning practical application. The application of the advanced models is one of the most powerful techniques to verify the mission of the investigating water wave, especially from the point of view of maneuverability. And thank you very much for your time.
Unfortunately, we've run out of time, so no time for questions, but I'm sure Mr. Amin will be delighted to answer any questions outside the session. No. Not one. Can I ask you again to join with me in thanking Mr. Amin for a very interesting, but slightly over length presentation.